We are going to look at some business applications now, and the first one that we're going to talk about is optimization. That means finding maximum and minimum values of functions. So the first problem that we're going to look at, you'll see now. The problem that you saw, always take out the pieces that you have to work with. So we found out it was about small televisions. The demand equation is P equals 110 minus 0.2 Q. So this says, depending on the quantity sold, that's the price that people will pay for it. Overhead costs are $500. The cost for each TV is $40. And the question said, find the price that will maximize profit. Now, when we look at these overhead costs and the costs for TV, they're talking about your expenses, and the overhead cost is a simple $500. That is the fixed cost. The cost per television varies depending on the number of TVs. That is your variable cost. The price that will maximize profit, well, let's think back. Profit is equal to revenue minus cost. Revenue is price times quantity. Cost is fixed cost plus variable cost. So all of this we've worked on this semester, and we have to take all this again and work with it after all those derivatives that we did. Maximize profit, that's why we need the profit equation. Revenue is price times quantity. My price is an equation. It's a function P. So my price times my quantity is 110 minus 0.2 Q times Q. My fixed costs are 500 plus the variable cost is 40 per television. So that has to multiply times the variable. So if we put this together, 110Q minus 0.2Q squared. Let's do the negative 0.2Q squared first. Plus 110Q minus 500 and distribute minus 40Q. So the actual profit equation is 0.2Q squared. 110 minus 40 is plus 70Q minus 500. That's my profit equation. That's what we have to work with now, so that we want to find the price that will maximize profit. So our profit equation, negative 0.2Q squared plus 70Q minus 500. To find a maximum, we use the first derivative. Remember that to maximize a function, relative extrema, first derivative. P prime equals, multiply by 2, negative 0.4Q plus 70. That's the derivative. So now I want to solve for Q. Set this equal to 0. Negative 0.4Q is negative 70. Q is equal to 175. That's the quantity that supposedly will maximize profit. Well, are we sure of that? Well, let's see. One thing we can do, we could put it on a number line and test on either side to be sure the function increases and decreases in the proper order so that this is a maximum and not a minimum. The other thing we can do is use our second derivative test. Take the second derivative, that gives me negative 0.4. Second derivative is negative, means the function is concave down. If a function is concave down, remember that the critical number that's in there, that's a maximum. So we know that this is a max at that point. So we do have a max profit at Q equal to 175, but is it the maximum profit? Remember that the absolute maximum can occur at a critical number, which is what this is, where the first derivative is 0, or it could occur at an endpoint. So we might think a little bit about the endpoints for this problem. Now, quantity has to be positive. Price has to be positive. So let's come back up here and look at that price and see exactly if we have limits on where the price is positive. If I take the price and I make 110 minus 0.2Q greater than 0. If you do that and you solve for Q, you find out that Q has to be less than 550. You do the inequality and solve. So Q actually goes greater than 0 and less than 550. So we know it's positive, but for P to also be positive, we're limited to those numbers. Now, if I plug those numbers, 0 and 550, back into my profit equation, and we'll plug in 175, let's just see what we get. If I find profit at 0, 0, 0, negative 500. If you don't sell anything, you have a loss, negative $500 profit. Now, remember, I'm plugging this into the profit equation. This is just money. Profit at 175. If I plug that number in for Q, both places here, I get 5,625. That is dollars. That is indeed a profit. So I do have a nice, so far, that's my highest number. If I go to my last point, my 550, and I plug that number in, P at 550 is negative again. 22,500 worth of negative. So it's not a surprise that this company wants to maximize profit because apparently they've had some losses. Now, what was the question? Find the price that will maximize profit. Well, I found that I do have a maximum profit at 175. I need the price, though, at that profit. How do I find price? Ah, there we go, right there. Price is 110 minus 0.2Q. I know what Q is at maximum profit. So to find P, I take my 110 minus 0.2Q, and I put in 175 for Q. And now we're going to go look and see what it is. So you can cut this little part. 75, how could I not remember that? So when you multiply out here, subtract from 110, we find out that the price is $75. So it cost them $40 to make a television. That was our variable cost. If they sell it for $75, that will give them the maximum profit of $5,625. For this business application, the problem asks us at what level of production will costs be decreasing the fastest. So this is not an optimization problem. It's not about max and min. It's about decreasing the fastest. So it's about rates of change. Now, let's review. If a function is decreasing, okay, a decreasing function, that means the first derivative is negative. Okay. Now, if it's decreasing the fastest, that means what we want is a decreasing rate of change. So we have two decreasings. So we take our derivative and the derivative of that to also be negative. We have a decreasing rate of change. Now think back about decreasing rates of change happened when a function was concave down. Remember, a function that's concave down had small negative slopes and then steeper negative slopes, so that the rates of change were negative, but getting bigger negatively, which means the rates of change were decreasing. And it turns out that they are the steepest just before it turns to be concave up. So our rate of change should be negative, but it happens just before a point of inflection. So what we want to do is to take our second derivative, set it equal to 0, and then find where it is decreasing, so we'll know exactly where it's concave down before it goes concave up. Let's go back up here now and take the first derivative and the second derivative. First derivative here, c prime of q. 3 comes around and multiplies, so we have 0.075 q squared, minus the 2 comes around to multiply, gives us 2.50 q, plus the derivative of 20q is 20, the derivative of 25 is 0. Now, I don't think anybody's going to be factoring this one. Maybe so. Probably you want to use the quadratic formula, so that our q would equal, let me put up the quadratic formula first, negative b plus or minus the square root of b squared minus 4ac all over 2a. A is 0.075, b is negative 2.5, our c is 20. So let's fill this in. So I have negative b, which makes it positive 2.5, plus or minus the square root of b squared, negative 2.50 squared, minus 4 times a, 0.075 times c, and all of that over 2 times a. And if you multiply all this together and take the square root and estimate, we end up with 2.5 plus or minus 0.5 over 0.15. So that gives us two values for q. Q is 13.33, and so on. And q could also be 20. So we have two possible values for our first derivative. Okay. Now, we can think about what to do about this. We know we have to go to the second derivative. We want concave down changing to concave up, which would be a max on the left and a min on the right. We could use these values. We can go directly to the second derivative. I'm going to take the second derivative. 0.150, 2 times 75 is 150, times q minus 2.50. Okay. When I do the second derivative, there are a couple things I can do. I can test to see if I have max and min, if it's going in the correct order, just by plugging in here. If I do that, I find that at this point, the second derivative is negative 0.5, and at this point, the second derivative is positive 0.5. That tells me that if I put those numbers on a number line, if the second derivative is negative, the function's concave down, negative second derivative, concave down. Positive second derivative, concave up. This is a polynomial, so I'm connecting it. So the point in the middle will be the place where concavity changes from down to up, and that is the point where it is the steepest. If I set this equal to 0 and solve, I get q equal to 16.67. And that does make the second derivative equal to 0. That is in the middle here. So at this point, I'd have the function, the costs decreasing the fastest. Q is the level of production. So this is the number that we need. For this problem, you really don't need to work through the first derivative to find your critical numbers, but it pretty much verifies what we're talking about. This one I can put on the number line and do a test on either side. Find C double prime at 10. Find C double prime, I need it in the middle here. Oops. C double prime, yeah. I could do 10 because it's easier than 13, and I need something to the right. I could do 20, which I've already done and found out that it's positive, which makes it concave up. So there's a variety of ways you can work through these. You can find the first derivative, skip directly down here, and put your number line on the second derivative, but you can also sort of verify what you're talking about. This would give you maximum cost. You don't want that, but this would be a minimum cost. And it's always good to know costs are decreasing the fastest at 16.67, that level of production, but your minimum costs occur when you're producing at 20 units. The last business applications that we look at are for elasticity of demand. You've seen it at least twice more, maybe 3 times more this semester already, and we're kind of pulling together a lot of different things that we've done since then. So let's think back. This is what we have for elasticity. Elasticity in general is the percent change in quantity demanded divided by the percent change in price. So we talk about how a 1% price increase affects demand, whether demand goes up or down. If price increases, demand always decreases. At elasticity equal to 1, that's unit elastic, there's not much change. Price goes up a little bit, demand goes down a little bit. They're pretty much the same. This is also the place where we have maximum revenue. So maximum revenue is up here wherever we have unit elasticity. So that's the same on both of these graphs. What I've done is put 2 graphs up here like in the lessons. Elasticities. 8 is -1. One graph is in terms of Q as our independent variable. The other is in terms of P as the independent variable. We can write any function in terms of P or Q, but the way elasticity relates for the inelastic differs depending on whether your variable is P or Q. Remember, there are 2 separate formulas for elasticity. Now let's look at this maximum revenue. Let's look at it over here first. The point in the middle is the point where we have maximum revenue. Think about price increasing. Price increases, so that moves from left to right. As prices increase, demand decreases. But if demand is inelastic, eta, absolute value of eta, less than 1. If demand is inelastic, revenue increases. So as price increases, when demand is inelastic, revenue increases. The ends go together. So when P is the variable, price increases, moving left to right, revenue increases, demand is inelastic. This piece is inelastic. So that when you hit the maximum revenue on the other side, as price continues to increase, revenue decreases. That happens when demand is elastic. That's for price. I always think of the ends as going together. Price increases, it's inelastic, and the increasing revenue all go together, and so the rest is decreasing. Now, we're going to turn that around for quantity, because if quantity is increasing, price is decreasing, And basically, everything is flipped. So we have our place in the middle where we have maximum revenue, and I have elastic when revenue is increasing, and it's inelastic when revenue is decreasing. Now, why do we need to use Q when we have P? Remember, this is revenue, and with revenue, we also talk about marginal revenue. As long as revenue is in terms of Q, that would be the derivative R prime of Q. That's what marginal revenue is equal to. Marginal revenue is very common in economics, so we have to talk about a marginal, and Q has to be the independent variable. Marginal is for one additional item, not a little bit more price. So at times we need to look at this graph, and at other times we need to look at this graph. So depending on the problem you're working with, you choose the independent variable to be Q or the independent variable to be P. For this question for elasticity of demand, we're supposed to look at the demand function, Q equals 100 minus 2P, and determine the price that will give maximum revenue. Now, you've been studying optimization, max and min problems. We can find the maximum revenue two different ways, using our optimization and also using elasticity of demand. It's always good when you can get to one answer using two separate methods. Let's first just look at thinking, here's a demand function, find maximum revenue. So we need a revenue function. Revenue is equal to price times quantity. In this case, the quantity is the demand function. So this is P times 100 minus 2P. So revenue is 100P minus 2P squared. To find a maximum, you take the derivative. 100 minus 4P and set it equal to 0. Doing that gives us P equal to 25. Now that's the only number that we got, but to be absolutely certain that this gives you maximum revenue and not minimum, you could either put that on a number line and pick a point on either side using the first derivative, or you could go ahead and take the second derivative, which would equal negative 4 less than 0. Second derivative negative indicates the function is concave down, which means yes, indeed, P at that price, 25, does give us maximum revenue. But this is a section on elasticity of demand. So how do we do this problem with elasticity of demand? Well, remember that maximum revenue comes from unit elasticity. So I can use my elasticity and find exactly what my maximum revenue is. And it's also possible that they would just give us the elasticity. But let's find it. Eta is equal to, now, P over Q, that's the way it always starts. But if I take the derivative here, it's Q prime. So I multiply by Q prime. That's the formula that I use. That would give me P, which is P over Q, times the derivative, which is negative 2. So my elasticity is negative 2P over 100 minus 2P. And it's possible that you could have a question that didn't tell you what the demand function was. That would just tell you, determine the price that will give maximum revenue if this is what you've got. You could probably figure out the demand function from the formula. Now, how do we find this unit elasticity? Unit elasticity says eta is negative 1, or absolute value of eta is equal to 1. So let's go ahead and take the absolute value of that. Absolute value of negative 2p over 100 minus 2p equals 1. Now for the absolute value, remember, p is already positive, it's price. This whole denominator was our q, it's positive. The only thing the absolute value does is take negative 2 and make it positive 2. So that's what we do next, is we solve this equation, multiply across, and we get 2p equal to 100 minus 2p. 4p is 100, so p is 25. That's exactly what we found earlier when we were trying to determine at what price do we have maximum revenue. Now, the other thing to think about is, suppose this is where we have our unit elasticity, but this didn't really tell us what happens if it's elastic or inelastic. That happens on either side of P. We know unit is maximum revenue equal to elasticity equal to 1, but what about if the question said where is demand elastic or where is demand inelastic? If you think about your graphs, and this time let's think about the graph where P is the variable revenue. And I have my revenue equation. And notice that the revenue equation that I'm using is a quadratic, but that's what you get if demand is linear, because when you multiply by your variable, you get a quadratic. Now for this equation, when we're talking about price being the variable, we have our maximum revenue at unit elasticity, and then we have inelastic on the increasing side. So if the question said, when is demand inelastic? Demand is inelastic for 0 less than P less than 25. But what about elastic? If we're on this other side over here, how do we know where it ends? Because it looks like it hits the end down here. So let's go back up and say Q has to be positive. Let's find out how far P can be, and we keep Q positive. Q greater than 0 means 100 minus 2P is greater than 0, means P is less than 50. 2 times 50, if I have any numbers less than that, 100 is bigger. So my p-values only go up to 50. That's what this looks like it ought to be, because it looks very regular. And so for elastic values for price, 25 is less than P is less than 50. There is an upper limit to what we can have for our revenue function before it drops below the axis and we don't have negative revenue. You can't have negative income. Okay? So we have two possibilities once we find our unit elastic. We can think about just on the left side, we know exactly what to have because price and quantity both start at 0. But on the right, for our upper limit, you just go back and find the value where Q is positive and you have an upper bound on the P, and that gives you the other interval that you have. We have this problem right here. A store can sell 10 items for $75, and the elasticity of demand at that price is negative 1.5. So what is true about marginal revenue? Now, when we talk about marginal revenue is the derivative of revenue with respect to quantity. So we have to think in terms of elasticity with quantity as the variable. Now, we're told the elasticity. We don't have to find it. We're given that eta is negative 1.5. Well, if you take the absolute value of that, it's greater than 1. If elasticity, the absolute value is greater than 1, that means elasticity is elastic. Elastic. When the absolute value is greater than 1, demand is elastic. So what does that have to do with marginal revenue? Let's think back about those graphs. We want to think about the graph where Q is our variable, and we're looking at revenue. Now, when Q was the variable, we had to think about if I have the maximum revenue here, where is elastic, where is inelastic? Elastic is on the left, on this side of revenue. What does this tell us about marginal revenue? Derivative is rate of change. So R prime of Q is the rate of change, and the rate of change is slope. So the slope of my tangent line is positive, so marginal revenue is positive. So as revenue increases, marginal revenue is positive. And that's what is true about marginal revenue for this function. The marginal revenue is positive. So marginal means sell an additional item. If I sell an additional item, my marginal revenue being an increasing function tells me that revenue is also increasing.